Okay, so we're going to take the principle of relativity and try to understand what it tells us about physics. And we need a mathematical framework in order to describe this. And the mathematical framework in which one discusses relativity is called spacetime. This is often introduced as some kind of mystical fourth dimension. I want to demystify spacetime. I want us to get very, very comfortable with it. So we're going to spend quite a bit of time getting comfortable with what spacetime means. So, all right, what do we mean by space? You can get into Kantian philosophy, but what we mean by space is all the possible places something can be. And we live in a three-dimensional universe, so all the possible places something can be are listed as, are labeled by three numbers. Pick an origin, pick some axes, measure the distance east, north, and up from that position, and you find all the possible positions an object can be, and the position of an object at a given time is given by these three numbers. We're studying mechanics, we're studying the motion of objects. To describe the motion of an object, you basically let your clock run, and at any given time, you specify where the object is. So to discuss the motion of an object, you need to compute or find or measure three functions: its position east and west, its position north and south, its position up and down. And you will remember to the days you were doing high school algebra that to understand such functions, you often plot them. You take the t-axis, you plot the function x as a function of t, and if you were describing the motion of an object which started at some point, say x equals 0, and moved up the x-axis and then stopped, and then moved a little bit down the x-axis and then you stopped studying it, then you would have drawn this graph of the function x of t. This is something we've all done. This paper, this plane in which I've drawn it, is spacetime. Spacetime is the place in which you plot the motions of objects. Now, in this case, I was plotting the motion of an object in one dimension. What would I do if the object were moving in a two-dimensional space? Well, then I'd have to specify both a function x of t and a function y of t. So what I would do, perhaps, if I were graphically talented, which I am not, is I would add an y-axis, and then at any time, I would plot x by moving my point up and down, y by moving my point in and out. And for example, if I study the motion of that object that was moving in a circle before, then the motion of the object would be in some circle in this xy plane. But as I plot it as a function of t, that would be like the motion of the object that we studied before was up and down the x-axis. When I plot it as a function of t, the object would, say, start here at t equals 0, and then move along the circle as a function of t, and I would be plotting, if I could draw, this sort of helical object. This would be called the world line of an object that is moving in a circle in the xy plane. Now, my graphical skills are not that great, so let's do a slightly better drawing and see what it teaches us. Here we have our friend, this time a green sphere, and it's going to be moving at a constant speed around this blue circle. And what I've done is I've embedded this circle, which is a two-dimensional space. The motion is in two dimensions. And I've embedded it in a three-dimensional cube where the vertical direction is going to denote time. It is indeed a curiosity of drawing space-time diagrams that rather than having the t-axis horizontal, it's our habit to have the t-axis be vertical. And so if I plot, the motion of this particle is going to be given by the green dot. There's going to be a red dot that will move, that will at any time, at any vertical position, be dropped at the place along the circle where the particle is at the time corresponding to that slice. And so as I plot this, the green particle moves around the circle, the red dot tracks it, and the red dot also is placed at any time at the vertical height corresponding to that time, and the net result is that I construct the helix that I was trying so unsuccessfully to draw. All this is the motion, if you want, the storyboard of the motion of this particle. Space-time is the place in which you draw graphs of x and y as a function of t. So let's study some simpler motions in space-time. What we're going to do here is we're going to have two dots moving around in our two-dimensional space. One is going to be moving up the x-axis and the other up the y-axis. The yellow dot moves slowly, and the red dot, as you can see, moves faster. What do the space-time plots of these motions look like? So again, I plot x and y as a function of t. I'll have a blue trace for the yellow dot and a green trace for the red dot. And what we see when we look at the world lines that we have drawn is, of course, they are plots of where the dots were as a function of time. And when we tilt it, we see that the slow-moving yellow dot generated a steeper trace than the more rapidly moving red dot. This is reasonable because over any interval of time, as between each time we plotted these spheres, the speedier red dot moved farther along the y-axis than the slower yellow dot managed to move along the x-axis. And we see that the traces, these world lines, these graphs, for both of these red and yellow dots are straight lines. They were moving in a straight line, and their world lines are straight lines. That's not exactly the same thing. In this diagram, what we're going to do is we're going to have the same red dot. It's going to move along the y-axis in the same straight line, but it's going to accelerate. What is that going to do to its world line? Well, when it's moving slow, its world line will be close to the vertical, and as it speeds up, its world line will curl away from the vertical, so that the graph that we draw is no longer a straight line, despite the fact that the motion of the object was in a straight line. Because it was not moving at a constant speed, its world line curved. So this is spacetime. Spacetime is the place where you plot r of t. Now, of course, I've plotted a one-dimensional motion, and whenever I'm plotting anything, it'll only be motion in one dimension, because I can barely plot that. The computer managed to do a decent job plotting two-dimensional motion. If you were really going to plot motion in a three-dimensional space, you would need a four-dimensional graph. We don't really have the technology to draw a four-dimensional graph effectively. We can't even imagine it, but we can mathematically describe it. And really, this fourth dimension is basically the statement that we are drawing three functions at once. There is nothing fancier about that. And so the points in space-time, the points in this four-dimensional graph, what are they? The points in space are all the places you can be. The points in space-time are all the places you can be at a given time. These are all the places, all the ways something can happen. What we call a given position in space at a given time is an event. It's a more specific statement than a position. So, for example, Durham at this particular time is an event. Durham is a location. Right now, my world line passes through Durham because at this point I am in Durham at this event. But Durham in 1985 is also the same location. It's a different event, and I was not there. And so a point in space-time is called an event. It specifies something happening or not happening, and through all of the possible places and times, you draw a one-dimensional line that is the trajectory of a particle. So we do not move in space-time. We do not move in time. These are all ideas that are confusing, that come from treating time in the same way that we treat space. What the extra dimension is that we add to space-time is basically the slices of the movie of our life, where you use the variable t to plot your position as a function of time. Hopefully that helps demystify this story. We've learned something about the geometry of space-time. We learned that if your trajectory in space is curved, then your world line will curve. The world line is this graph of all the positions that you have occupied over the course of some time interval. So if the object is changing direction of motion in space, then its world line, tracking this change, will change its direction as well. If an object is moving in a straight line, then its world line will not have to change direction, but if the object accelerates, the world line curves towards or away from the vertical as the object is slowing or accelerating. What does that tell us about an object whose world line is straight? Well, an object whose world line is a straight line in space-time is an object that is moving in the fixed direction at a fixed speed. Aha! What we have is a geometric description of Newton's first law in space-time. Space-time gives us a nice geometric description of objects, the world line of an object upon which no force acts is a straight line in space-time, and conversely, an object whose world line is a straight line in space-time is an object upon which no forces act. So space-time is useful. File that away. We'll come back to it. So here is the version of space-time that I am able to draw. We imagine a one-dimensional universe. Objects are free to move to the left or to the right along this x-axis. We plot their motion along x as a function of t. As usual, we have the t-axis vertical, and so there are some names that you might give to all things. So all of the points in this graph that are, I've picked some time, t equals 0. So the coordinates of a point, an event in this graph, is given by its x-coordinate and its t-coordinate. X gives you the distance from some particular point, which I've called x equals 0, at which this event occurred, and t gives you the time after some particular time that I decided to call t equals 0, when this event occurred. So give me an x and a t, and that tells you if something happened at that position at that time. You've specified where and when it happened. So all of the x-axis here are all of the events that happened at the time t equals 0. By convention, I'm going to call that now. What are all the events that occurred at the position x equals 0? Those are all the things that naturally would be called here. So the t-axis might be called here. The x-axis might be called now. And what we saw is that the world lines of objects that are moving at a constant velocity are going to be straight lines. Your instantaneous velocity is essentially the slope of your world line, but the slope is measured from the t-axis. So it's a sort of backward slope because we put t vertically. So if you take this red world line, that describes an object moving to the right. It starts at this negative time way over here to the left, and then it moves to the right. And if you look at this green world line, it describes an object which moves faster. You could measure your velocity by taking some time interval. Notice that I've arranged, and we'll often do that, for both objects to be at the same place at the same time at t equals 0. They were both at x equals 0. If these were material objects, they would have crashed into each other, with the green object overtaking the red object and slamming into it, but they, in this case, pass right through each other and continue moving in a straight line. And if I take some time delta t later, and I measure where these objects have gone, you can see that in the time delta t, the red object has gone this distance, delta x red, and the green object has gone the larger distance over here, delta x green. This is telling me that the green object is moving faster than the red object. This is what we're saying. What does it mean for an object to have a vertical world line? A vertical world line means x as a function of t is constant. The blue object is a stationary object. It sits at the same location throughout time. What does it mean to have a horizontal world line? Nobody has a horizontal world line. A horizontal world line is a collection of all the events that happened at the same time. So just as the x-axis is what I called now, the orange axis might be what you call a little bit later. These are a collection of all of the events along this line, are all the things that happened at a particular time. So at this particular time indicated by the orange line, the blue particle was where it always was, the red particle was at this position, the green particle was at that position, and so on. I said that space-time is the right place to discuss relativity. Let's see what relativity looks like in space-time. So what I have here is space-time as seen by some observer. Their axes are drawn in black. I will use a green pen to denote their observations because I don't have a black pen. So this is the black observers now. This is the black observers here. And I have here a world line that is tilted to the right. That means it's the world line of something moving from left to right at some constant velocity along this diagram. And what this is going to be is the nose, or the origin, as seen by another observer. The blue observer thinks that this is here. What he thinks of as something that is stationary is going to be something that is moving relative to the first observer. This is precisely the situation that relativity describes. The world is observed by an observer in the black axis, and the world is observed by someone else who is moving at a constant velocity relative to the first one. And the statement is that the laws of physics, as observed in the blue system, should be the same as the laws of physics as observed in the black system with the green notations. And so we have arranged things so that at the time that the black axes select as t equals 0, we've picked that time to be the exact instant where, along their motion from left to right, the blue observer passed the location of the black observer. And moreover, we have set it up so that at that same time, both observers started their clocks. What this means is that the blue observer considers t equals 0 to be the same as what the black observer considers. So they agree on what now is, and then they measure time with synchronized precise clocks from that moment on. And what happens then is that if there's some event going on, somewhere over here, an event occurs, a birthday party takes place, well, then the black observer measures when and where the event occurred, and he declares that it occurred at a distance x from the place, from the origin, and at a time t. What does the blue observer measure? Well, it's clear that the blue observer measures a different distance, since the blue observer is at a different position at the time the party occurred. He measures the party to occur at this distance to the right of his origin, and he also measures the time at which the party occurred. And since they synchronize their clocks, they agree on the measurement of time. So they measure for the same birthday party the same event, the same time, but they disagree on where the birthday party occurs. It's not that they disagree, but they describe it with different coordinates. The position to the right of the axis, or the origin, at which the moving observer measures the party differs from the distance from the origin that the black stationary observer measures the party to be at by a quantity that is Vt, where Vt is simply the distance over here by which the two origins differ, and it changes as a function of t because over time the blue observer is moving to the right. I can invert these relations and figure out how to find the description given by the stationary observer in black, given the data of the measurements of the moving observer in blue, and you can solve these linear equations rather easily for x and t as functions of x prime and t prime, and it's not surprising that these equations look the same, except the sign of v is changed. What this means is, the black observer sees the blue observer moving to the right with speed v. If the blue observer were to describe what the black observer is doing, they would find that the black observer is moving to the left with exactly the same speed. There is not a difference in principle between these two systems. What they measure is the relative velocity. V is not some absolute object. It's the relative velocity. The blue observer is moving, say, to the right in this picture relative to the black observer, or equivalently, the black observer is moving to the left relative to the blue observer, and physics does not select who is right about this. This is all very logical, and I am indeed belaboring the obvious, but let's belabor it one more time. Let's understand what this tells us about an important topic called velocity addition. So here's the same collection of two observers with their heres and nows, and now I've introduced the world line of some other object here. And this object is also moving to the right in this picture. It's moving faster, it turns out, than the blue observer, so that it's moving to the right both with respect to the black observer and with respect to the blue observer. But the blue observer can measure its velocity. Notice this is a straight world line. The motion is inertial motion with a constant velocity, and as the blue observer measures it, this velocity is given by some number in meters per second, u prime. Now, both observers will agree that this thing is moving. They will not agree on its speed relative to them. Let's compute the speed with which the black observer measures, the speed that the black observer measures for this green object for which the blue observer measures a speed u prime. Well, how do we do that? This equation describes the motion in the blue observer system, and the coefficient gives us the velocity. Note that I have selected a particularly nice world line for the green object. I have set it up so that the green object meets both observers at the same time that they meet each other. We will often discuss such things. Discussing an object which makes the same motion but meets the observers a little bit later or a little bit earlier is not that much more complicated, adds an unnecessary algebra step, so we won't deal with it. And so, how do we transcribe the motion as seen by the moving observer to the motion as seen by the black observer? Very easy. We know the relation, we wrote it in general, between the coordinates as observed by the observer in black and those as observed by the observer in blue. And given x prime and t prime, you can figure out x and t. Now, we need to plug into this the information we have, which is that x prime is u prime t prime. So I plug that in, u prime t prime plus v t prime. I collect terms and write that as u prime plus v t prime. And then I remember that since they synchronized their clocks, t and t prime are the same thing, and I reach the conclusion that x is u prime plus vt. Oh, good. This is an equation of exactly the same form. It describes an object moving at a constant velocity. Excellent. Inertial motion, remember, physics should not change between frames. If one observer says no force is acting on the green object, the other observer agrees. No force is acting on the green object. Its motion, its world line is a straight line in both frames. Its motion has a constant velocity, and that constant velocity is just obtained by adding the velocity as measured from the moving observer's viewpoint with the relative velocity between the two observers. This is not that anything. I mean, this is not saying anything that you didn't already know. If you are standing in a train that is moving 100 miles an hour and you are walking at 1 mile an hour in the direction the train is moving, relative to the ground you're moving at 101 miles per hour. This is so obvious. Why did I take so long to discuss it? We'll see why it's worth discussing in a minute.